Hello, this is a video to help you guys with the life cycle of a star storyboard. If you've already gone through the Think Central, you'll know some of this stuff, most of this stuff, but I know the Think Central is kind of a lot of information and hard to understand. So this is just kind of a secondary video to help you be able to figure that out if you need. So, and it also gives some good ideas and things that kind of some heads up on things that we're going to learn next week about gravity, inertia, things like that. So here we go. So life cycle of a star, as I said in my other video, stars are not alive. We just kind of refer to them as the life cycle and born and die and stuff like that because they go through kind of like phases and changes like a living thing, but absolutely 100% not alive. So what is a star? A star is simply just what it's made of is gas. It's just a really, really, really giant mass of gas. Most stars are hydrogen and helium combinations, but later in life, especially the bigger ones, start to be composed of heavier and heavier elements. We often say that they're on fire or they're burning, but that's very much not a fact. It's not actual fire. I saw a little joke, a meme on Google Images as I was searching for some pictures for this slides, and it joked that how can they be burning? There's no oxygen. Well, they're not. They're actually going through a process called fusion, which is actually even hotter and releases more energy than a fire, and we'll talk about that later. So one thing just to know kind of as background information here is that there's a very strong relationship between mass and gravity. So once again, mass is how much stuff something has. So for example, I've got the moon, the earth, and Jupiter, three very different masses. The moon is about a fourth the size of the earth in mass, I think. Try and remember that. And Jupiter is way bigger, 300 times Earth. So my picture here does not justify to scale. So one thing is just if there's more mass, there's more gravity. So if you've ever seen footage of astronauts jumping around on the moon, the spacesuits that they're in, they would not be physically able to walk on Earth in, and then on the moon they're jumping up in the air feet because the moon's gravity is weaker. It's a smaller mass, therefore it has less attraction. Gravity is simply an attraction of one mass to another mass. So technically, you have gravity. The only thing is you can never escape the Earth or other planets or the sun that has a massive, bigger gravity. So when you drop your phone, unfortunately your phone doesn't fall and stick to you. It falls to the ground because the Earth's mass is stronger. It creates a stronger gravity. So just to know that bigger stars are going to have bigger gravity, and the more mass just is more gravity. So that's a main kind of driving force of how these life cycles work. Another thing that's kind of a key thing here. So for the difference between high mass, low mass, well, high mass, I'm using cars because I speak car. Cars kind of relate to this. So if you think of a Hummer, like the actual Hummer H1, they're huge, they're big. Gas tank size is 28 gallons, where a Geo Metro, if you've ever heard of it, that's a 90s car, very tiny, very, very tiny. They have a gas tank size of 10 gallons. So much smaller in mass, much smaller in fuel, so to say. So same is true of a large mass star. It's going to have a lot of gas. It's going to have a lot of mass. So it's a lot of power, and it's a lot of, so to say, fuel. Where the small stars are a low force and a low amount of fuel. So how does that relate to how long they can live and how quickly they go through their changes? Same thing here. So if we take a look at MPGs, mile per gallon, Hummer is going to get 10 miles per gallon. Very poor. Because it has lots of power and it has lots of, can do lots of big extreme things. Whereas the Geo Metro actually can get, best reports I've heard, is 60 miles per gallon. So that's really, really good. I don't know why they stopped making it other than it was kind of tiny and dorky. But miles per gallon, for the whole tank for the Hummer, is going to be 280 miles total. Even though it's big, it's powerful, it has 28 gallons of gas. That is a big receipt for filling up, except for right now it's so cheap. Whereas the Geo Metro could actually go 600, so more than twice as far. So how this relates to stars is that the big stars are going to transition through their phases really quickly, and they have a much, billions of years shorter lifetime Whereas the tiny stars, the tiniest of the tiny, the lowest mass, like ones that are like 10% of our sun's mass, we haven't actually really, science hasn't really seen those end yet. So that's kind of still a mystery of what happens to them, because they're kind of like the Prius of stars, and they don't run out yet. So that's kind of a mystery. Whereas parts of the high mass ones, we can actually see some of their phases occur in our lifetime within a year or a month. All right, so overall, they both begin over here. This is your first question on your worksheet, by the way, so be using this to help your worksheet. Feel free to pause if you want and stop it and kind of come back and forth from your worksheet here, or just watch all the way through and then go to your worksheet. So they all begin, both large and small mass stars, as nebula. And this picture doesn't quite do it justice. Nebulas are very, very big. They're very spread out. They are full of various gases and dusts, and kind of just, it's basically like a dusty space cloud. Those, like I said, gravity, mass creates gravity. So the different little pieces kind of begin to snowball, and little piece and little piece and little piece begin to collect and collect and collect until there is a big enough center mass that kind of draws that cloud together. So that collecting snowball time is going to be the protostar. And that's when it's like chunks and chunks are building. For stars like our sun, during the protostar time would also be the time period that it formed the planets. And if you know about the difference of the inner and outer planets yet, like the first four, Mercury, Venus, Earth, Mars, versus Jupiter, Saturn, Uranus, Neptune, you'll know that there's kind of a rocky group, the inner ones, and a gaseous group. And there, because as that process of drawing together happened, it kind of left gases in the outside and brought the heavier stuff, the solids, to the middle. So that kind of explains that. So protostar is when it's beginning, but it's not actually really lighting up. The fusion hasn't begun. But both, if you notice, the high mass and the low mass both begin as the nebula, then turning into the kind of the nebula or the protostar. Okay. Then we begin here, so many places just call it this. We call these two parts here, refer to them as main sequence stars. On your worksheet, we're referring to them as the adult star. A star stays in this part for the longest of time. That's a majority of its life. That's kind of why we're calling it the adult, because if we look at humans, we spend the most years as an adult. All right, so let's take a look at what's actually happening during that, like what kind of causes it to become a main sequence star and what it's doing during the main sequence star time. So if you saw in the Think Central, I stole this picture from there. So these dots over here are going to be representing hydrogen with their protons, electrons, and the gravity of the stars. They're so big as that protostar becomes more and more like snowball collected. It becomes so great of mass that it has so great of gravity that it actually begins to smash the hydrogen molecules. So if you remember from the periodic table of elements, those are number one. So they have one proton, one electron, one neutron. So it begins to smash so much that it can cause the hydrogen to actually come together. So I know we normally don't say like things can become other atoms. Well, inside a star they can. So fusion is that one exception that two hydrogens, so 1 + 1, can combine to become helium-2. When they do that, it's not just a happy little math problem of 1 + 1 = 2. It's actually an insane release of energy. So this is what actually causes them to transition from that protostar into the main sequence star, is that the hydrogen gases start to get smashed into the helium. Now this is like high school or college level stuff. So the main thing is you just need to know that the energy from a star comes from the changing of the gas elements inside. That's really all you need to know. Okay, so this is what causes it to become a main sequence star, and this is all it's doing during those for many billions of years in this time. Our sun is currently in the main sequence time, and it's doing this, and it'll keep doing this for well past when we're dead. Okay. Another thing here, just kind of looking at all of these processes are a never-ending fight between this fusion, which is creating an insane amount of heat and energy and reactions, and that's kind of wanting to explode the star out bigger. However, the mass of the star is kind of keeping it together. So it pretty much is a constant and a stable kind of balanced forces throughout this time period of it being a main sequence star. If you look at, for answering your question on your worksheet here, if you look at, there's tons of options for main sequence stars. It's kind of this little banner stripe through the center here. We've got other ones that you're not going to refer to, so like Sirius you've probably heard of, is a white dwarf down here. That's going to be later in the low mass sequence. So main sequence is going to be any of these. They can have a spectrum of blue, white, yellow, red. Most are kind of in the white and yellow, okay, and it's all dependent on their temperature and their gases. The higher ones here, the giants, that's probably red giant, and then super giant. Don't pick those ones for the question on your worksheet. Pick one of these. You can refer to one of those. You can pick, do you want to have one that's blue? Do you want one that's white, yellow? Okay, here's the sun, so don't pick it. Our sun is in size, in actual size, it is a medium. In brightness, it's kind of a medium. It's pretty much just kind of an average star in mass, in brightness, in everything, which is good. If it was bigger or smaller, our lives would be different. So it's kind of happy. It's just kind of a medium average star. So you can pick ones down here that are smaller, less bright, more reddish color. You can pick a white one, blue ones, any of those you could pick for your worksheet, okay? Those are all main sequence stars. Like I said, though, don't pick super giants, red giants, or white dwarfs. Those are not an adult star, okay? So back to here. So far, large mass and small mass have pretty much been the same. The beginning, nebula, protostar, and now main sequence star, now is when they begin to change. So the reason that they transition from main sequence star is that they've pretty much finished the process of hydrogen becoming helium, and they've gotten into like a majority helium and nearly no hydrogen left. And so it's just kind of time to go on to the next phase. And because of that, their mass and their density is changing. And that for a low mass one, we'll continue on first here, okay? So low mass stars, their next step, so like our sun, the next step would be to go into a red giant. So a red giant is going to be giant, obviously, much bigger. I've heard some estimates that if the sun, like when the sun turns into a red giant, it'll expand from its current size out into the size of Jupiter's orbit, which is massively larger. And that, of course, would take out Mercury, Venus, Earth, Mars, and the moon on its way. But that's billions of years, estimated billions of years from now. So no worries to us, but it is a massive difference in size. So basically, because it's now the fusion inside it has changed, it's lost the gravity, and kind of the energy it's releasing is now winning. And so that the forces are unbalanced and it begins to explode out bigger. Also, its temperature, because it's bigger, is actually lower. And you can see here now it's a red color instead of yellow, which red is colder than yellow, okay? Still very hot though. Then, after the red giant phase, we go into planetary nebula, which is one of the most beautiful ones here. Notice in the center, so kind of it exploded out to that big red giant. Now it's shrinking back in. As it shrinks back into its next step, which is going to be the white dwarf, which is this little white dot in the center of each of these like eye looking things. As it shrinks in, it kind of leaves some of the dust and remnants behind, and those kind of glow as these beautiful colors and kind of give it this like cat eye like look. Once all of that eventually does draw in and get collected, it's done with the planetary nebula. I don't know exactly why they call it this. It's not forming planets. It's not anything special like that. We just call it planetary nebula. So you can research it if you want to know more about why, but it's not like making new planets at that time. Okay, the very, very end. So after planetary nebula is kind of boring from there on. So it collects all that dust, all that colorful glowingness into the very center. It's a much smaller size than the original like sun or original main sequence star was. It's much smaller, it's much lighter, it's not as hot, it would have less gravity. It's kind of starting to become lame and nearly dead. Then once it's a black dwarf, basically it's done with all of its fusion. It can't create any more elements anymore. Nothing else is combining. So therefore no more heat is getting released, no more light is getting released, and it still exists. Like, it's still a chunk of matter, but it's not releasing anything anymore. But don't get confused with black hole. It doesn't have an intense gravity to draw anything else into it. For the most part, it's just a chunk of non-glowing elements left in space. So it pretty much just dies in its end. It totally depends for how long this takes. It totally depends on how big it is. So I want you to use Think Central or your workbook pages or Google to make an answer for yourself, depending on how big you were kind of guessing that your pretend star in your storyboard is. Okay, let's continue on with what would happen after main sequence star with a high mass star now. So we're talking about one much bigger than our sun. Our sun's medium, so this is things bigger than our sun. So here's a picture of our sun. What would happen to not our sun, but another main sequence, or another high mass main sequence, is that it's going to turn into, oh, this is a super giant picture, or a red giant picture, sorry. So it'd be even greater than this. So that's a good one for red giant. But so for supergiant, it's going to be the same story. It has a higher mass. So the explosion out into the thing is just bigger. So supergiant is basically a larger red giant. Nothing special there. Because of the largeness, it starts to make more higher, heavier elements and things. Same story here, except for it's not just a shrinking back in like the planetary nebula. There is a huge explosion of the supernova. Probably the most gorgeous thing, in my opinion, out in space is supernovas, and they can happen. Most other events in astronomy take beyond our lifetime amount of time, like thousands or millions or billions of years to occur. Supernova is one of the cool, rare things that actually like scientists have been able to watch and observe it happen. The higher the mass of the star, the quicker it happens, kind of like the Hummer scenario. It's going to run out of gas faster. So this is something that's actually been observed like twice over history, at least according to my research, and we can watch it happen. So it's kind of cool. So a supernova, like I said, is an explosion out with all those gases and dust, and then it kind of begins to collect back in, just like the planetary nebula. So it kind of leaves this remnants around the edge that glows. So very pretty. Next, there's two alternate endings of a large mass star. So if it is less than, like it's bigger than the sun, but it's less than 10 times the sun, it's going to end as a neutron star. Sorry, I didn't put titles here. It's going to end as a neutron star. I like this. This is totally computer made, but I like this picture here of kind of representing how small it is. So neutron stars go from things super, super, super big, like so much bigger than our sun, which is so much bigger than Earth, shrinking it down to actually smaller than the Earth. However, it still has all that matter. So it's very small, but it is very, very, very dense. So there's one YouTube out there that, and based on science predictions, that claims that a spoonful, so like if you could take a neutron star, which you couldn't, and scoop a spoonful, a regular, spoon of the star, that would have the same amount of stuff as a cruise ship. So a boat that can, is a hotel basically for 4,000 people with, a water park and a movie theater and, restaurants galore. All that stuff in a spoonful. So that's how compacted this has shrunk down. So its amount of gravity is just insane, and it's going to draw things into it around it. But it's not great enough to be capturing the light that it's producing. So a neutron star is different than a black hole because it's still releasing light and sound. If you've studied astronomy much, you know that things in space, we listen for them too. So over here with a black hole, if you look on Google, there's tons of images of black holes. None of them are legit. We just recently got a photo of a black hole, and it's very basic. Black holes, most pictures are going to be computer made like this one, but basically they're more than 10 times the size of the sun in mass, and they've shrunk in so much that the gravity of that tiny, very, very, very dense chunk of matter is so great that everything is attracted into it and nothing can escape. So like if we sent, like student representative from 8th grade Dakota Hills to go in and tell us what a black hole is like. When you're falling into the black hole, you try to text us a message, it would actually take in your text, like the Wi-Fi signal. You scream for help and it sucks back in your sound. You turn on your flashlight to do, some blinking for us to know SOS, and it sucks that back in too. So nothing escapes. So the only reason to really know and can study black holes is that it's like an emptiness. It's like a spot that nothing is coming from in space. And that's only produced by the biggest of the biggest stars dying and collapsing into an absolute tiny, tiny, kind of, some people call it a singularity spot that just has the greatest gravity of anything in the universe. So there's not many of those because there's not many of the stars big enough to do that, but some in. So on your scenario for your storyboard, if you want to pretend that you have one of the biggest of big stars and yours dies as a black hole, go ahead. Just consider that the bigger your star, the shorter its lifetime. It's like a Hummer, it's going to go through it faster. But do some research and actually give legit numbers on that. Don't just make up like, oh, it's 1,000 years old. That's not. Okay, so hopefully this helps. If you have any further questions, please go ahead and message me. Otherwise, this hopefully helps you get that done. Don't stress too much. I didn't mark it as due until Sunday evening. So, not much more to do over the weekend. So if you need to spend some weekend time to finish, go ahead. Don't stress. I don't mark anything late. So good luck. If you have any questions, message me. Thanks.